Hello, folks. This is lecture 7 of the mechanical vibrations course. And essentially, we are entering a new phase of the development of the course in vibrations. These are the items that I would like to discuss. And the first one is undamped force vibration, but under a very special type of a loading, which is sinusoidal loading or harmonic loading. And then we go through items 2, 3, and 4, which are discussing the concept of resonance. And we're going to initiate the process of introducing damping into the problem so that things get a bit more complicated than what is done in one. Okay, let's start with undamped. That means no damper, no friction, frictional effect, essentially. Forced means that a load F of t is applied to the mass. So far, we assume that this mass is displaced and released from some kind of a condition, either rest or giving an initial velocity, and the mass goes back and forth indefinitely if it's undamped, and the amplitude dies down if it's damped. But here, there is an external force also acting on the mass. Okay, that is the difference. So force means that there is a force acting, and harmonic load means that that force has a very special type, as you'll see in a minute. Okay, so when you look at the free body diagram in the x direction, for example, the force F is acting, it's an external force. Kx is force of the spring, so the mass feels that is pushed to the right by F of t and pulled to the left by K of x, and there is a tug of war between these two, which causes the vibration. So under the free vibration, the right hand side would be 0, but under the force vibration, under this very special type of loading, is F naught cosine omega t. You might wonder, well, in how many situations do we actually have base harmonic force? Well, actually, you'll be surprised. Just be patient, we'll get there. Okay. The first thing I'm going to do, although I can treat the equation exactly like on the first line, but in all likelihood, if this was, if and that's probably the way it would have been done if it was handled by your differential equations course. But it is also helpful if we divide that top equation by m, and when you do that, obviously the coefficient in front of x double dot will be 1, and you have k over m, which is actually omega n squared. And finally, this little f naught is the ratio of big F naught over M. Okay. Now, we are going to look for a particular solution to this equation, which is also harmonic with exactly the same frequency. Okay, so we claim that the solution to this equation, the particular solution to this equation that you see up there, is like that, except that I don't know what X is. Big X. Big X, which is the amplitude of this solution that I'm claiming it to be, is unknown. So we're going to take this, differentiate it twice, and stick it in there, and hopefully we can find what X is. Big X is. And sure enough, you differentiate this thing twice, you get big X omega squared. Omega squared. Remember, this one there is an omega n here. There's a distinction between this omega and that omega n. Please do not make the assumption that this omega is the same as omega n at this point in the development. Okay? So omega and omega n are different animals. So you write it here, and notice that the nice thing is that cosine of omega t cancels from both sides, and you can solve for big X. So big X is just little f naught divided by omega n squared minus omega squared. Those who don't believe me, if you take this guy times cosine of omega t and plug it in the very first equation, you get equality. And that should not surprise you, because that's exactly how we got this big X. All right. So as long as omega is different from omega n, this makes sense. Okay. When omega is equal to omega n, this is all nonsense because we have big X equal to something divided by 0. And that does not make sense. All right. If omega is in fact equal to omega n, we have to use a different particular solution. This is no good. All right, let's move on. This is just a matter of taking x of p and plugging, taking big X and plugging it in the expression for x of p, and you get the final solution, particular solution, all looking at you right there. The solution to the top equation on the left corner, the particular solution is equal to right here. Or you can say, of course, not even, you can say that the solution to the top equation, the second top equation on the left hand side is equal to this. Okay. Now, sometimes, notice that the general solution is made out of two parts. The particular solution that you got and the general solution. That general solution is when you set the right-hand side equal to 0. This is all a flashback from differential equations. So the general solution to the equation is when you set the right-hand side equal to 0 and solve. And we know all about it. Let me actually go ahead and remind you what the equation was. If x double dot plus omega n squared x equal to 0, the solution to that is sine and cosine of the frequency omega n. That's all I'm saying here. Now, that particular thing can be done in two different ways, and you should be prepared to handle both. Whatever is needed is more convenient. You can either write it out like that, an unknown constant times sine of omega nt, plus another unknown constant times cosine of omega nt. And then the rest is the particular solution that, of course, you got here. You can write it like that, or you can write it as big A, unknown, sine of omega nt, sine of omega nt plus a phase angle. And this, of course, you can write it as big X, because that was big X, omega t. The point is right here. You see this? This is the solution to the homogeneous equation plus the particular solution, either written like that or as a big amplitude sine of omega n t plus a phase. And we don't know big A, we don't know phi. Okay? And then the rest. Okay? These two are saying the same thing. And if you ever wonder, let me remind you what you do. You expand sine of sum of two angles as the product of sine and cosine plus cosine and sine. And you rename, for example, big A sine of omega nt as A2 and big A cosine of omega nt as A1. And you get this. All right, let's move on. Both A1 and N2 depend on the initial condition and the phase and the initial velocity. And the same thing, big A amplitude and the phase depends on the initial conditions. Now, if you gave me x naught and t naught, if you gave me x naught and v naught at a certain time, initial condition, for example, at t naught equal to 0, or any other t naught, as a matter of fact, but we're looking only the case t naught equal to 0. That's why you put a 0 here. Okay. If you gave me those values, I can take x of t either from here or from there, x of t, plug in 0, get an equation involving A1 and A2, and differentiate this thing, set again t equal to 0, get another equation for A1 and A2, and solve it. It's algebra. And the same thing down here. A lot of algebra. And if you do that, that first form will look like this. You may or may not believe it, but Inman has worked it out. and with a little patience, you can work it out and get your answer. So here is this V naught is the initial velocity. This X naught is the initial position. Okay. And of course, you know what omega is. Little omega is the frequency of the harmonic load that you're applying. And everything we know in this formula. Remember, this omega is referred to as the driving frequency. And of course, omega n, for the last 3 weeks, we have learned it's called the natural frequency. Let's do an example. We have a 10 kilogram mass attached to a spring with a given stiffness, and it's being driven by a harmonic force whose frequency is twice the natural frequency and an amplitude of 23 newtons. So let's see what it says. Assuming that the mass starts from equilibrium position with initial velocity 0.2 meter per second, get the solution and plot the response. Now let's make sure we understand what is given here. This is M, mass of the block. This is K, the stiffness of the spring. This is big F naught, the amplitude of the driving force in Newton. And omega, you're told, is twice the omega n. Okay? Assuming that the mass starts from in equilibrium position, that says X naught equal to 0. And this says V naught equal to 0.2 meters per second. So it's just a matter of calculating the stuff and plugging it into the equation that we got in the previous slide. There's no memorizing that. Write it down or bring it with you. So omega n is root of k over m. So omega, the driving frequency, is twice that. We're told that. So it's 20. Little f naught is big F naught over m. So 23, big F naught is right here, divided by 10, mass of the block, 2.3. And this thing is something that we need, because remember, the amplitude of the solution will be this. So it has F naught, little F naught, 2.3, divided by omega n squared minus omega squared. We know what these things are. We get that number. Initial velocity, initial position is 0, because we are told that this starts from the equilibrium position. We did not displace the mass. We just let it sit there and then moved it and gave it an initial velocity. I'm sorry, did not move it. The block was sitting there. We did not move it. Right where it was sitting at the equilibrium, we give it an initial velocity. So X naught is 0 and V naught is 0.2 meters per second, which is given up here. So these are things that we need to plug into that horrible expression on the previous slide. Okay? Remember, it had two parts. It had two parts. It had sine and cosine of the omega and t type. And there was this expression, that guy, times cosine of omega t. These two are omega n. This is omega. And you can plot it, and it looks like that. I just noticed, yeah, it just looks like that. The only thing is that here I've combined the sine and cosines, okay? I put the cosines together, there's absolutely no reason to write it like that, but there we are. So you can see that it's a rather complicated situation, complicated solution, all right? It's no longer only sine and cosine. You have a whole whack of sines and cosine, even of different frequencies that are involved. When I say a whole whack, it's 3, of course. Now, let me remind you, this is the repeat of slide 5. And it's so important that I put it here. And notice that here, this is undamped, the solution to the undamped problem. Guess what? When you have damping there, this is going to be more complicated, okay? When I say complicated, it doesn't mean hard. It is just that uglier and longer and more involved, because damping is going to pop up in there too. Okay? All right. Let's go ahead and I think this is not supposed to be there, so M is unknown. We'll get there. So here's another example. We have a force vibration of a mass attached to a spring of stiffness 2000. So we have the stiffness of the spring, and it's being driven by a 20 Newton harmonic force. So at 10 hertz. So this is the driving frequency. This is omega, not omega n. Omega is 10. Big F naught is 20. We are given the stiffness. We are given stiffness of the spring K. If the maximum amplitude of the vibration is measured to be 0.1 meter, okay, and the motion is assumed to have started from rest, find the mass of the object. Notice that the only thing that's not given here is the mass, and we are supposed to find it, and the information, the data that we need is given, and it says that the maximum amplitude is 0.1. If we observe that the maximum amplitude is 0.1, find the solution, find the mass. So the first thing that we do, we essentially have to go to that ugly expression on the previous slide, plug in the stuff there, make sure that the maximum x is 0.1, and out of that, get m. Okay? So let's see now. What do we know here? The maximum amplitude of vibration is a big X. Let me remind you, we assume that the solution, no, hang in there, is I better correct myself. It is not quite right. Now, let me remind you that the solution is made out of two parts. The solution has a homogeneous part. Remember, there were two ways of writing it. Do you remember that? There were two ways of writing it. Plus the particular solution. What we know is that the maximum amplitude of that sum is 0.1 meter. Okay? Yeah. Now, the only thing is that in that problem, if you go back to the slide, notice that x naught is 0, v naught is 0, right? Let's go back here. Let's see what happens when x naught is 0 and v naught is 0. V naught is 0, first term gone. X naught is 0, this term is gone. Okay? This term is gone. And we are left with what? We are left with, this is not there. We are left with minus F naught over omega n squared minus omega squared cosine of omega nt plus this thing cosine of omega t. The point is that that term times cosine of omega nt plus this term times cosine of omega t. Okay? And it's written for you right there. So that ratio, first of all, we know, just plug in your F naught. See that? Your F naught, this is your big F naught. You have your little F naught. Okay? And you have your omega squared. You have omega squared. Omega is 10. Omega is 10. You don't know what omega n is because you have the you don't know the mass. Okay? But from the previous ugly slide, there is the expression for x of t. You can write it like that. Remember, there were two cosines present. Okay. And by the way, this is fine. And by the way, these two can be combined as the sine times sine. From trigonometry, when you have the difference of cosines, you could have combined them into product of the sine of the sum over 2 and this over 2. So this, from trigonometry, these two cosines can be written as twice that product. Okay, so Either way. Now, when you look at this combination, that expression here, that expression is the maximum amplitude of vibration. And you are told that this combination, you are told that this combination is 0.1. Okay? So this thing is 0.1. So what do we know here? We just write down whatever that we know. So what is this combination? Little f naught is big F naught over M. And of course, omega n squared is k over M. And of course, omega squared is omega squared. We know that. We don't know M. We know the k. We know the F, big F naught, as you're told, is 20. And you know that this is given as 10 hertz, which is in radians per second, 10 times 2 pi squared. Right there. The only unknown in this expression is M. And you solve it. And that solves the problem. It is kind of misleading because when I said that the amplitude of vibration is 0.1, okay, you might have said, well, how did you know that this is the amplitude of the vibration? Well, that is not obvious. This is the amplitude of vibration in this problem, but by no means is obvious. So the explanation is given on the right hand side here. Initial velocity and initial position equal to 0. This is a solution. From trigonometry, these two can be combined into sine, and then it becomes obvious when you combine these, you get a factor of 2 that is put up here, and this is the maximum amplitude of vibration. This is the maximum amplitude of vibration. That's what I put over there. Okay? Please think about it, because it is not obvious what this is. It is not the big X, because big X is only the one that goes with this piece, cos omega t. So when you write them together and you combine them there, it becomes clear what the maximum amplitude of vibration is. It's right there. And you start from here. All right. So now we're going to discuss the case where omega n and omega are close to each other. Not necessarily equal to each other. Well, not equal to each other, but close to each other. So, let's see. Let's assume that to explain this thing, let's assume once again that the initial position and initial velocity are 0. In other words, this starts from equilibrium position with no initial velocity, and the force is acting on it, and it's going back and forth. Okay. Well, you already saw this thing in the previous slide. Okay. So X is going to be made of 2 pieces. It's exactly the same thing that I had on the right-hand side in the previous slide. And this from trigonometry, magic of trigonometry, the sum of 2 sine, the sum of 2 cosine, the difference of 2 sine, the difference of 2 cosine can be using the trig identities can be written as this thing times 2. So this parentheses up to is that product times 2. Just take the 2 in the front. That's what it is. Okay. So let's see what happens when omega is very close to omega n. First of all, if omega is very close to omega n, this combination, see that? This combination is essentially becomes either omega, it's become 2 omega over 2 times t, either becomes omega t or 2 omega, or omega t or omega nt. Very close to it, at least. So, if this difference is small, that difference is small, but this difference is large. The sum is larger than that, for sure, because these are being close to each other means that this difference is small compared to the sum, which is large. So if we look at that expression, if we use this and look at that expression written here again, this, you see that frequency? You see this frequency? This is small, right? Omega n minus omega over 2 is the frequency. If the frequency is small right there, the period is large. This sign has a large period. Okay. All right. And this has a small period because of what we just said. Compare these two. This is small, period is large. This is large, period is small. So that's what this is saying. So when you plot something like that, it's a sinusoidal one. It's not sinusoidal, but it's a periodic one, as you can see. One of them has a large period right there. This has a large period that goes with this difference, and the other one has a small period, which is these things, okay, which are these wiggles here. So let me put it this way. Second term is responsible, because look at the frequency is large compared to that. Second term is responsible for these spikes. And the first term is responsible for this variation, slow variation, because it has a large period. So rapid oscillation with a slowly varying amplitude is called beat. Rapid oscillation with a slow varying amplitude is called beat phenomena. And by definition, omega beat is the difference of omega n and omega. That's the definition of omega beat. Please don't divide this thing by 2 and say that's omega beat. That is not. Omega beat in our textbook and in majority of places in the literature is defined as the absolute value, the difference between these two frequencies. Okay. So here's an example. I have plotted the graph of cosine itself with this frequency, 4.4 hertz. This is the plot of sine with 4.4 hertz. Omega n in hertz is 4.4. That's why I multiplied by 2 pi here. This is omega, which is a little bit different. So instead of 4.4, this is 4 hertz. Okay? So it looks like that. Notice that it is the smaller frequency. That's why you can see there's a difference. But when you look at that combination, sine of difference over 2 times t times sine of sum of the two divided by 2 times t, it looks like that. So this is the beat phenomenon. It shows you the beat phenomenon. Okay. Omega n, omega, driving frequency are close to each other. The response is going to behave a beating phenomenon. And the beat frequency is just absolute value of this number minus that number. There we are. Obviously, if you want to find the period of the beat, you just usually take this divided by basically 2 pi divided by omega beat. You're going to get 2.5, and you can see that. Look, 2.5, 2.5. There we are. Okay. Now let's look at the case where the driving frequency omega, right there, is the same as natural frequency omega n. All right. So here's my equation. This omega on the right hand side happens to be square root of k over m, which is your omega n. Let me remind you that what we did, we divided through by m. We wrote it like that, where k over K over M is omega n squared, and of course, big F naught over M, we call it little f naught. Now, if this omega is the same as that omega n, that solution does not make sense. Because what we did in the previous few slides, we showed that if you go by that route, your big X actually becomes something divided by omega n minus omega, and that thing becomes zero, and that does not make sense. So this is no good. But somebody has come up with the actual solution. Now, if you ask me, well, how the heck did they know this? That's the outcome of 300 years of mathematics. Okay? 200 years, 250 years of mathematics, calculus, etc., differential equation. So, if omega is equal to omega n, this is no good. The solution that you should be looking at is t. That's the important thing. T, time variable, times unknown x, sine of omega t. Okay? Now, if you take this and just like before, plug it into the differential equation, this differential equation, realizing omega and omega n are the same, there's no distinction on how you write it, you're going to come up with the following solution. So the solution, the particular solution becomes f naught, you know what f naught is, divided by 2 omega, you can call it 2 omega n or 2 omega because they're the same, 2 omega, times t times sine of omega t. And if you still don't believe me, take this, plug it in there, you see that you get equality. So the key is putting this t in front of that expression, and don't take cosine, take sine. All right, oops, let's go back. So that means that the general solution is going to be the homogeneous part. And notice that I'm not writing this as omega nt and omega nt because omega and omega n are the same. So I wrote it like that. And then finally plus the particular solution that by magic, somebody's got it to be this. All right, let's move on. Now, the case where omega equal to omega n and the initial conditions are given can be written like that. Because notice that in this expression, if you set t equal to 0, this guy will go away, this guy becomes 1, and this goes away. So you get x of 0 equal to x naught. And if you differentiated this and then set t equal to 0, believe it or not, you're going to get x dot at 0 equal to v naught. Okay? Initial velocity, initial position, and of course, this is the driving frequency, the same as the natural frequency. Okay? Good. And if you plot this, if you plot that, notice that you get a solution that is whose amplitude is increasing with time. You see that? There is a little t here. As time, little t gets bigger and bigger and bigger, this amplitude f naught over 2 omega, that's a constant, times t becomes bigger and bigger and bigger. And this is what we call resonance. In other words, when the driving frequency matches the natural frequency, you're in trouble. So the amplitude becomes unbounded as time goes on. I mean, if there is too much displacement of the mass, then of course the spring eventually will fall apart, right? That makes sense. That's loosely, in a very naive and layperson version, say that the spring will fail and break, etc. So yeah. All right, so a problem here. Suppose that we have a simply supported beam like that, 4 meters long, and the cross section is given 3 by 6. there's an electric motor here sitting up there, which has an imbalance, and therefore, because it has an imbalance, it actually will create a harmonic force of some magnitude. Now, this is why I said harmonic forces are not that unusual. In fact, motors with imbalances will create that harmonic force in a way. Okay, it says at what speed, at what RPM, uh, do we expect wild oscillations of this simply supported beam? Okay. Now, the information about the material properties of the beam is given here. Obviously, without that, you can't do the problem. So we know its density and we know its Young's modulus. So basically, we have a harmonic force acting on a mass. There is a mass. I mean, loosely speaking, if we pretend that the mass of the whole beam is the mass that is being represented in our model, and then there is a fancy spring here. We know the stiffness of that spring. This is what we did 2 weeks ago. So this simply supported beam on the transverse vibration can be viewed as a fancy spring with a stiffness 48 EI over L cube. We did that. These are things that you should know, and you have your notes, and you go back to it if ever needed. Now, what about the mass? Well, the mass is the volume of that beam. I mean, we are making an approximation that this is the whole mass of that beam is going to participate in the vibration. There are secondary assumptions that one can make to make a better model. And ultimately, a finite element model will take care of it, but not in this course. So the volume of this beam is BHL times the density is going to give you the mass. You work it out, you get 56.16 kilogram, 7,800 kilogram per meter cube. The dimensions, the width and the height of the beam are given in meters. So 3 centimeter and 6 centimeter in meter. This was 4 meter, and this is what we get. Now, the eye is bending about the higher axis, the taller axis. So it's going to be BH cube. Make sure you know what B is the width, H is the height. Okay, so you just plug that in. This is the mass moment of inertia about the central the center of mass of the axis coming through the center of mass of the beam. You just plug into that stuff, 48 EI over L cube. We are given 210 gigapascal as the Young's modulus, which is steel basically. I, we just calculated, L is 4 meters, you get that number. And now natural frequency is the square root of K over M. The mass of the beam, stiffness of the beam as calculated above, 38 radians per second. That is the natural frequency. You don't want the motor to match that speed, okay? Now, obviously, it says how many RPM, so we have to convert this information to RPM. So 60, see, this is radians per second, radians per second. Okay, if you want to do it in terms of minutes, it's going to be 60 seconds, and you divide it by 2 pi, you get cycles per minute or RPM. 363. Do not let that motor operate at speed of 363. Now, incidentally, real life, there's damping present. In real life, you may have to operate at speed that are higher above that. Sorry, are higher than that, above that. And therefore, you have to go, if you want to reach that speed, you have to go through that anyway. So the moral of the story is that in real life, make sure that if you want to increase the speed above that, you don't keep the switch at that speed or keep the knob at that speed for very long. Go through it very quickly. Okay. We haven't done damping yet. We will. Okay. So we're not going to do the entire case of situation with damping today. But I'm going to give you the basic picture or the big picture of what will follow on Thursday, for example. So we have a mass spring system here, but there is also a damper present. Remember, the last 40 minutes, we didn't consider the damping. It was all force vibration of an undamped system. Now we do. So we are giving this thing an initial condition, maybe it's sitting at zero, and we are also applying a harmonic force to it. So this is the big picture. A harmonic force of this given magnitude, that driving frequency, applied to the mass, and maybe some initial conditions. I mean, if you start from equilibrium position, the mass is sitting there, you start from that equilibrium position without giving an initial kick, then of course the load applied starts moving around. But in that case, starting from equilibrium position at zero velocity, these two are zero, but they may not be. Okay. Now the general solution is just like before, made of two parts. One of them, a particular solution to this, and the other one is a homogeneous solution. What do I mean by that? You make this right-hand side zero, you have mx double dot plus cx dot plus kx equal to zero, and you know everything about that problem. That's the first 2 weeks of the course. Okay? Now, the particular solution, we still have to work on it. Don't know how. But anyway, let's assume that somehow we have done it. So the homogeneous solution plus the particular solution. By the way, while we are at it, this is also referred to as transient solution in vibration, which dies down because of damping. And this is the persistent solution, stays there. That particular solution is called steady state solution because it stays there. This dies down, this stays there in the long run. So there we are. Now that fellow, as I said, the first 2 weeks of the course, maybe third lecture or something like that, third or fourth lecture, we did it. It was like this. It was like that. Okay. There is an exponential term that is dying down. There's an exponential term that's dying down. There is a damping frequency. Remember, it was omega n square root of 1 minus zeta squared. Do you remember that? And there was an ugly expression for phi and an ugly expression for a, which incidentally, at that time, because we didn't have anything on the right-hand side, involved initial conditions. But you cannot use those things because now we have the forcing frequency also, the forcing term also. Now, I only do this thing today, okay? The whole thing together and doing examples, we're going to leave it until later on. So this is what is called the steady state solution or the particular solution, okay? And we already did this when there was no damping. That's already taken care of. Okay, so now we're going to look at the case where there is damping present. Okay, there we are. Free body diagram. The only additional term is the damping force on the left side. So here's the mother of all equations. If you want to clean it up, write a different form, you can divide by m. If you divide it by m, this thing was omega n squared. K over m is omega n squared. This thing we called little f naught. So big F naught over m we call little f naught. And this thing became 2 zeta omega n. These things we have done in lecture 3 or lecture 4. All right. So omega n, of course, is root of k over m, and zeta is the damping ratio, which is the damping value here, divided by either you write it as 2m omega n, this is the critical damping, or you can write it as 2 square root of km also. Incidentally, some books, they don't use the letter C, they use the letter B. Okay? So they're interchangeable. Now, the big question is, what is the particular solution? So let us assume the particular solution looks like that. Just like before. Remember, we did exactly that. 300 years of mathematics is helping us. Okay? The only difference between this and what I had before, there was no theta and there was no c, right? There was no c there. C was 0 on that. I'm talking about the last half an hour, the initial half an hour of the presentation today. But here, you need a theta. Big X is unknown. Theta is unknown. Okay. If you want, and it will be perhaps easier if we did it like that. Remember, cosine cosine of the difference of two angles can be broken down into the product of the cosine plus the product of the sines. Okay, so I'm talking about cosine of omega t, sine of theta, plus sine of omega t cosine, sine of omega t, sine of theta. Okay. Now that combination of big X times cosine of theta, I can call it AS or AS. And the other combination, which is big X times sine of theta, I can call it BS. So instead of fooling around with big X and theta, what I'm going to do, pretend that this is expanded in uh, as the sum of two and just written like that. So we don't know AS, we don't know BS. Just like here, we don't know X, we don't know theta. It's just that we wrote it like that because it's easier to handle. Okay, so we know the expression for XP right there. So differentiate it again, second derivative, stick it in the mother of all equations. Remember, the mother of all equation, we wrote it two ways, with m, c, and k present, or with divided by m, so that there's only omega, n, and zeta present. That's why that second form is a little bit easier. So there is no magic way. You just have to do this. You just have to take these, stick it in that equation, and collect terms. So we have something involving cosine of omega t, this big bracket, something involving sine of omega t, this big bracket, equal to 0. And this is supposed to be 0 for every t. The only way that can be true for every t is that if this bracket is 0 and that bracket is 0. This is it. You get two equations and you have two unknowns. What are the unknowns? AS and BS. Two equations, two unknown involving AS and BS. These are all known values. These are all constant known values. And lo and behold, you can solve it. Somebody has done it for us. There we are. So we know everything about the particular solution. Remember, the particular solution was this thing times cos omega t plus this thing times sine omega t. Yeah, you can write it like that. But then again, using the concept of something times cosine plus something times sine of the same frequency, remember, you can combine it into a big amplitude and a phase. There we are. Right there. Remember how its solution was? Big X cosine of omega t minus theta. And I said that it's easier if you introduced it in a different way, AS and BS. Get AS and BS, plug it back in XP, clean it up. It's all trigonometry, and it's all elementary trigonometry. I don't mean anything advanced. Okay. There we are. So this is a problem. They have a structure, a one-story building. The details of the structure are given to you as far as the stiffness of the columns, and we are assuming that the total stiffness of the column, if there are two columns here, this, otherwise there's four columns, for example, maybe this is a shell or something, the sum of the four columns is going to be that. Stiffness of the four columns is going to be that. The structure, it has a mass, this top, assuming that there's the mass, this is the mass of the roof, 100 kilogram. You can think this is a table. And then it's subjected to a force, harmonic force of amplitude. This amplitude F naught is 500, and it's operating at 50 RPM. No, 15 rad per second. This omega is 15 rad per second. Let's assume that there is a damping present, or maybe either artificially introduced or made actually a damper somehow placed in there of that damping ratio, or you model this thing and come up with a conclusion. After doing experiment, you come up with a conclusion that damping value is this. Remember, this is a single degree of freedom. You can estimate the damping by logarithmic decrement. And remember how it was. You let it vibrate, plot something, and out of that something, get the logarithmic decrement. So we did it and came up with 0.1, or somebody has done it for us. Okay. So, first of all, we are looking for the steady state, for the steady state solution. Steady state solution means that the damping, after damping dies down, that XP. Okay, but I'm going to do the whole thing. The amplitude of the steady state displacement, the phase with respect to the exciting force, that means the little theta. Find the little theta. Find the maximum velocity of the response. And for these initial conditions, get the total response. So A, B, and C do not depend on the initial conditions, because these are only relevant to the steady state. I mean, it says steady state, etc. So these are relevant for a steady state solution. It's only the last part that it says, give me the total solution. So I not only need the steady state one, the particular solution, but I also need the homogeneous one or the transient one. Okay, and I need initial conditions for that. Okay, let's move on. That is the data that was given to us. Mass of the roof, or the top of the table if you want, amplitude of the harmonic force applied, the damping ratio somehow arrived at by experimentation or otherwise. This is the frequency of the driving frequency, and this is the stiffness of the structure. So let's find the natural frequency, square root of k over m. And because we're given damping ratio, we can calculate the damping frequency. Now remember, this damping frequency is going to only show up in the transient solution, not in the steady state. The steady state solution has exactly the same frequency as the driving frequency, 15. Okay, just keep that in mind. F naught, little f naught is big F naught over m. There we are. Well, you have no choice. Go plug it in. Big X equal to, stuff was given to you 2 slides ago. Big X equal to this. There's not much you can do. You just have to go back there and plug it in. And theta, 19 degrees. 0.33 radians or 19 degrees. Now we can write this is the whole solution for the particular. So we just found the big X. We just found theta. This omega is the same as the driving frequency, 15. It's just a matter of plugging it in. So notice that I have also done the homogeneous one for you, or the dying down solution. The steady state solution is right here. This is the steady state solution. Okay? Frequency 15 radians per second, the phase with fog. This is the transient solution, the one that's going to die down because of the damping, and that depends on initial condition. The C1 and C2 will depend on initial condition. Okay? Yep. So to find C1 and C2, what we're going to do, we force it. In other words, you plug in t equal to 0 in this expression, we get a value. And notice that that plays a role also, because when you set t equal to 0, this is going to be part of the game. And then you differentiate it and then set t equal to 0. And you're told that initial displacement is 0.06, but the initial velocity is 0. So this is just ugly algebra that hopefully you plug it into your programmable calculator, or just do it patiently and come up. All right? It's just algebra. There's no way around it. That's as simple as that. Okay? And keep in mind that problems like that popping up on a test, for example, I fully understand that if you got to this point and it's just that you got wrong values of C1 and C2, as long as it doesn't dramatically affect something else, I understand that. We take that into consideration, and it's not going to be a major issue. Okay, so yeah, there we are. Ugly, but there's not much you can do. You just literally write it down. The first piece that has exponential in it, right there, the first two terms, these first two terms, which incidentally, if you insist, it can be combined into a single term involving sine, and there's going to be a phase, and phase is going to be, of course, difference from that, etc. But you can leave it like this. And this is the transient or the particular solution, or steady state solution. This is the steady state solution. This is the transient solution. And it's plotted. So look at the transient dying down because of the exponential, negative exponential term in front of it. This is the steady state, never dies down, goes at the same frequency as the driving force. And if you add these two, initially there is some disturbance, because initially this guy plays a role, but after a while, transient becomes so small that when you add it to this, it shows you essentially a nice uh, alternative description of that. There we are. So, what I would like to discuss now is the concept of phasor diagram, or a graphical representation of what happens for a single degree of freedom system which is going under vibration when a harmonic force is applied. Okay. Let me uh, show you this figure, but how how we can relate to the concept of force vibration that we have done a few minutes ago. So here's the situation. The applied force is harmonic, right there. F of t equal to F naught cosine of omega t. We can think about this as a vector which changes with time in this two-dimensional diagram. Notice that it has amplitude F naught, this purple one, see that? There's the F naught. It has amplitude F naught, magnitude F naught, and it has angle omega t with the x-axis right there, omega t. As time gets bigger and bigger, this vector, purple vector F naught, begins turning and turning and turning, etc. So you give me t, I have an f naught of a given magnitude, f naught, and a position which is determined by the time that you gave me times omega. Now, the response x of t, steady state response x of t, looked like that. Go back to the slide 5 slides ago where we made a guess of the solution. Okay? It has a magnitude x. There's the magnitude x. It's this green one. And it's theta degrees before f. See? This was f. Theta degrees before f. Right there. Before f. Right there. Smaller angle. So it's omega t minus theta. Right there. And it's turning. Obviously, it is turning because you're saying theta degrees before omega t, before f, omega t or f is turning, and before f is turning. Okay, so there we go. So this is the phasor representation of the steady state response, the green one. Now the spring force is, remember, the spring force is always kx of t, k times x of t. So if you take the displacement vector multiplied by k, you get this blue one, which is the spring force. The spring force is like this, right there. Applied harmonic force, steady state response, theta before, it has a phase, and kx is along x, but multiplied by k. Now, let's go to the velocity. The velocity is the derivative of this, but the derivative of that is negative. Omega comes in the front. This actually, I'm sorry, this is not x dot. This c should not be there. Let's clean this up. Let's go back here. This c should not be there. This is the damping force. I should see now. I should do this thing as c times x dot. C times x dot. Okay, and yeah, that's fine. It's fine. Yeah. Let me take this c out. Maybe it's better if I took this c out and this c out. Okay, that's good. Let's go back. Let's go back. All right. So this is fine. So you take the derivative of this, you're going to get that. Derivative of cosine is sine, and there is omega in the front. So there we are. Okay. Now this sine, I can write it as cosine, except that I have to add 90 degrees to it. This is just the fact that cosine and sine are 90 degrees apart. So here's what happened. Look at x dot. Now, what is the damping force? The damping force is c times x dot. C times x dot. So if you take c times x dot, you're going to get, look at this, the magnitude of the damping force right here. This is the damping force, which is 90 degrees ahead. This is the 90 degrees ahead of the displacement right there. This is displacement 90 degrees ahead. So that's why it looks like that by 90 degrees. The magnitude of it, this red vector, the magnitude of it is damping force, which is c x dot. Here is x dot, omega times x times that, times c omega x. Here's what happened. Applied harmonic force, steady state response, green. Applied harmonic force is that purple. Steady state response is green one. Spring force is K times the green one, which is this blue dashed one, Kx. Damping force is 90 degrees ahead of this. spring force, magnitude C omega. Okay. Another way of looking at it, this damping force comes velocity. Velocity leads the displacement by 90 degrees. You remember that stuff? Okay, there we are. And if you take the second derivative of x, of little x, you get omega squared times x, and that's the inertia force. The inertia force is that black one. There's a minus sign here, so it's also 90 degrees ahead of velocity, which means 180 degrees ahead of the displacement, which means totally going in the other direction. Right there, minus. And these things close. So this is the mother of all equation. When you have a harmonic force on the right-hand side applying, and this is called a phasor diagram. All right, so let's write these things down. This is the displacement. That is the purple one, which is the force, harmonic force right there. This is the mother of all equation. That is the harmonic force. You can see that. This is the displacement right there, 30 degrees behind. Okay. And when you multiply it by k, you get that guy, kx cosine omega t minus theta. That means that this, see that this projection is just x times cosine, right? This is the angle omega t minus theta. But anyway, move on. Kx is take this thing and multiply it by k. Take the green one, multiply it by k. You get the blue one. This is the damping force. And it's drawn for you right here. The projections are drawn for you here. Okay. And here is the inertia force. Mass times acceleration, basically, which is right there. And it is, whoops, which is right here. So if you look at this expression, the sum of these will be equal to the projection of that on the horizontal axis. So this is resolving everything on the horizontal axis. Okay, and you get that equation. This is called the phasor diagram. Phasor diagram is very common in electrical engineering because actually this vibration problem that you're doing is very, there's a one-to-one correspondence between this and when you have alternating current and sources and the resistor, the capacitor, and inductor and things like that, there's a one-to-one correspondence between these things. Okay, that's why whatever we do here, in some sense, is equivalent to things that are done in a what is it called? Inductor RLC circuit under harmonic under alternating loading. Okay, good. Let's move on. Now, a couple of comments. When damping is small, the value of C is very small. So this red one, which represented damping force, has a small size. You can see that. And there's a very small phase difference when damping is small. There's a very small phase difference, for example, between the applied force and, let's say, the displacement, for example. Okay. And obviously, because this red thing is a small, this red damping force is small, the energy dissipation by the damper is small too. In the limit, when there is no damping, okay, I'll come back to that in a second. In the limit that there is no damping, this red one is zero, it's not present, and this is an undamped phasor diagram, undamped representation of the phasor diagram for our problem. Incidentally, this last line here, in the case of very small damping, see, these are all true. This last one is the input energy provided by external force goes into kinetic energy and potential energy. Okay? All right. So because damping force is very small, that doesn't do much. So whatever is given by external force F is going to go into kinetic and potential energy. One to stretch or compress the spring, the other one is the kinetic energy of the mass. Okay. Now at resonance, that theta is 90 degrees. That phase difference is 90 degrees. Okay. So the phasor diagram at resonance becomes this rectangular shape. The phase difference becomes 90 degrees. The phase difference between the applied force and the displacement becomes 90 degrees. Another way, there are other ways of saying this thing. So, for example, they say, or we can say that uh, all the external energy provided by F, that harmonic force, is absorbed by the damper. It all goes into damper. Whatever comes into the system, it all goes into the damper. And another way of saying that the inertia force actually always balances the spring force. Okay. Phase difference 90 degrees. I already mentioned that. Inertia force is completely balanced by the spring force. And that's it. That's it for today, and see you on Thursday.